Hey, this is Horner. We're going to look at the solutions to section 16.4 problems. We have a small sphere for number 27 with a charge of negative -0.6 microcoulombs. It's placed in a uniform electric field of 1.2 times 10 to the 6 newtons per coulomb pointing to the west. What is the magnitude and direction of the force on the sphere due to the electric field? So for this one, a few things that we've got to recognize. One of them is this, we need to get into standard notation. So this will be negative -0.6 times 10 to the -6. That's micro, and then it's coulombs. And we know that this is the charge. They want to know the magnitude and direction of the force on the sphere due to the electric field. So we've got our sphere here. We know the electric field is pointing due west, so it's going in this direction, and that would be our electric field E. Let's go ahead and solve this. We know that force is equal to Q times the electric field strength. Our Q is -6 times 10 to the -7th coulombs, and we're going to multiply that by our electric field, which is 1.2 times 10 to the 6th newtons per coulomb. And if you do your math, you should end up with 0.72 newtons. So since the electric field is pointing to the left, and we have a negative charge here, so it says a small sphere, here's our sphere, it has this charge, and the electric field is going in this direction, then we know that the force has got to be going to the east. So it's got to be going in the opposite direction. Now, the reason that you can figure out it's going in the opposite direction is that electric field looks like this around the sphere. So here's your sphere. This side has got to be positive, and this side's got to be negative, and your electric field is traveling in this direction. So if I have a negatively charged particle, the force is going to be towards the positive plate because opposites attract. And that is the end of number 27. Let's go ahead and take a look at the next one, which is number 28. The electric field across a cell membrane is 1 times 10 to the 7th. It's directed into the cell. So if a pore opens, which way do the sodium ions flow, into or out of the cell? And then they want to know what is the magnitude of the electric force on a sodium ion. And they tell us that the sodium ion charge is positive E. So for letter A, since positive charges move along the direction of the electric field lines, the sodium atoms should flow into the cell. So if this is your cell membrane, and we know that the electric field is traveling in this direction, so it's going from a positive region into a negative region. So this is positive, and this is negative. Sodium ions are going to flow in the direction of the electric field, so they're going to go across the membrane. It's because they're trying to get away from the positive region and trying to go towards the negative region. So your answer here should be into the cell. For letter B, they want to know what is the charge. They want to know what is the magnitude of the electric force. So once again, just like in the last problem, force is equal to Q times E. And here our Q is positive E times E. The E stands for the elementary charge. So for this, it's going to be 1.602 times 10 to the -19th coulombs. And we're going to multiply that times our field strength, which is 1 times 10 to the 7th newtons per coulomb. And when you're done, you're going to end up with a force of 1.6 times 10 to the -12th newtons. And do notice that it says it just wants magnitude, so we don't have to worry about direction in this problem. And that is number 28. Let's go ahead and move on to number 29. For number 29, they say what are the magnitude and direction of the acceleration, so we're looking at acceleration, and they want both magnitude and direction of a proton at a point where the electric field has a magnitude of 33 kilonewtons per coulomb and is directed straight up. So here we have our proton, which is a positive particle. The electric field is going straight up, so we could say that on the bottom we do have a positive region, and on the top we have a negative region. and so our electric field lines are moving in this direction. We can see also that the direction for this proton should also be in the up direction. It'll be going with the field lines because the positive and the positive region are going to repel each other, and then the positive and the negative region should attract each other. So it should have a force in this direction. For the magnitude, we need to go ahead and figure that out. We know that for number 29, force is equal to Q times E, and because we're dealing with an elementary charge here, we can just say E times E. And we also know that force is mass times acceleration. And so that's equal to the elementary charge on the proton times E. And if we rearrange this, we get the acceleration is equal to the elementary charge times the electric field strength all over the mass of that proton. The E field, we had to look it up, is the charge on an electron on a proton is 1.602 times 10 to the negative 19th. The electric field, they told us, is 33,000. So you have to make sure you get that kilo converted into just regular newtons, 33,000 newtons. And we're going to divide that by the mass of a proton, which is 1.673 times 10 to the negative 27th kilograms. If you go through and do your math, you should end up with 3.2 times 10 to the 12th meters per second squared, and that should be in the same direction, so we're going to say up. Since it asks for both the magnitude and the direction, if you don't have the direction, you'll miss a point. So you would definitely want to make sure you have your magnitude with the unit and then your direction, which is up. So that one is number 29. Let's go ahead and take a look at number 31. It says, what are the magnitude and direction of an electric field midway between 2-point charges, negative 15 microcoulombs and positive 12 microcoulombs, that are 8 centimeters apart? So first thing we need to do is let's just draw this situation. So here I've got a plus 12 microcoulomb, and over here I'm going to have a negative 15 microcoulomb, and these are 8 centimeters apart. So at this point we know that this is 15 times 10 to the negative 6th. This is 12 times 10 to the negative 6th because micro means times 10 to the negative 6th. And then this is 8 centimeters. We want it in meters, so this will be 0.08 meters. Now we have everything in the units that we need. We need to find the electric field, and so our electric field here is going to be E is equal to K times Q all over, and then it's our distance squared. So this is the just the normal equation for electric field. We need to look at this for both of the charges. And so we're going to say for charge 1, so let's call the 15 microcoulomb negative 15 E1, and then we'll call the positive 12 E2. So we're going to do this twice, and then we're going to add the two together. So E here is equal to 9 times 10 to the 9th times the charge, which is negative 15 times 10 to the negative 6th. And then we're going to divide it by the distance between the two squared. But the problem that we have here is they want us to find the electric field midway between the two. So we're really looking at how it affects this middle part right here. So we want to know what is the electric field on the star. If we want to know the electric field on the star, we need to take our position, which is 0.08 meters, and divide that by 2. And then we're going to square that. And it's because from here to here is 0.04, or 0.08 divided by 2. So that's for E1. For E2, we're going to do the same thing. It'll be 9 times 10 to the 9th. We're going to multiply that times the charge, which is 12 times 10 to the negative 6th. And then you have to divide that by the same thing, which is 0.08, since this is also 0.04. 0.08 divided by 2, which is at 0.04 squared. At this point, we have everything we need. We've just got to go through and solve this. So if you go through and solve, we need to take 9 times 10 to the 9th and multiply it times negative 15 times 10 to the negative 6 divided by 0.08 divided by 2. And that would be 8.4375 times 10 to the 7th. Now we need to go ahead and do the other side. And you should end up with 6.75 times 10 to the 7th. This one's actually negative. I forgot about that. Now we can go ahead and solve for the final answer for this one. And it should be equal to negative 1.5 times 10 to the 8th newtons per coulomb. And because it's negative and this is the negative value, we're going to say it is toward the negative 15 microcoulomb charge. So it is going to the left since it's negative. And that is the end of number 31. For the next one, which is number 33, this one's a little bit easier. It says rank points A through E in order of magnitude of the electric field from largest to smallest. So the electric field is the largest, closest to the charge. So A is closest to the charge, so it's first. The next closest would be B. The next closest out of C, D, and E, now we have to look at the distance actually from the charge out to the letter. So C would be next, and then we can draw a straight line here. That would make D next, and then finally this is our furthest charge away, which would be letter E. So that's how we rank those points. These are just arbitrary points. Notice the field lines are strong here. They're close together, and we're really close. Here the field lines are much further apart, so letter E has got to be our least. And that is the answer to number 33. Let's go ahead and take a look at the next one. Next one is number 35. I have positive point charges Q, so here's Q, and 2 times Q are located at x equals 0 and x is equal to 3 times D, which would be right here. They want to know what is the electric field at x is equal to D, so which would be point P. So we're measuring from the left side. To do this one, we're going to say the electric field at point P is going to be equal to, and now we need to find the electric field due to each positive charge. So we have 2 positive charges here. So for the first one, we're going to say it's K times Q, and we're going to divide by D squared. And then we're going to subtract the other one. Since these two are both positive, they push each other apart, and so our field lines are going against each other. So this would be K times the absolute value of 2Q, and we're going to divide that by 2D, since our distance from P over to this Q is 2D, and from this one over is just D, so that's where that came from. And when you do that, you should end up with this is equal to K times Q all over D squared minus, now we're going to split this up, this is going to be K times Q over 2D squared. And so now that is equal to K times Q all over 2D squared. And they want to know which way would it be pointing. And so the electric field at point P should be pointing to the right. So that field should be pointing towards the right. The next one is number 36. They want to know what is the field at point S. So for point S, we're going to do a very similar thing that we did before. So let's go ahead and say E here is equal to, oops, that doesn't look like an E, so let's go back. This is E, the electric field, is equal to K times Q all over 2D squared. Okay, so that's from this charge affecting S, and that 2, it's actually 2D, and then that quantity squared. Then we're going to subtract from it K times 2Q. So here's our other charge affecting S, and the distance to it is only D squared. So now we can go ahead and simplify. So this would be K times Q all over 4D squared minus 2 times K times the absolute value of Q all over D squared. And if you do a common denominator, D squared common denominator for both, and then add them together, you should end up with 7K times Q all over 4D squared. So common denominator, you'd have to take this side, multiply it by 4, so that makes this the top and the bottom by 4, so that puts 4 on the bottom, and then 4 times 2 would be 8. So now we have 8/4 minus 1/4 is going to give us that negative 7KQ all over 4, and then this is a D squared. And they want to know which way this one goes, and this one definitely goes towards the left because this is the bigger charge and you're closer to it. The reason that, let's go back to number 35. In 35, the reason that the field goes to the right, even though this is a bigger charge, remember distance is a bigger factor than charge is. And so because P is closer to this one, then that's why the field goes to the right. But for this one, for letter S, the field is really going to the left. We're very close to a larger charge. And that's why you see what you do. And so 40, this one, it says sketch the electric field lines in the plane of the page due to the charges shown in the diagram. We know that we always go toward the negative charge and we always go away from the positive charge. So for this one, if we're going to start at the negative 2 Q charge, we know we've got to go towards it. So let's actually start at the Q charge. And if we start here, we're going to have a straight line go in like this, and then all the other lines will curve a little bit. So that one curves in, this one curves in, and you'll notice that the strength of the field is really strong at the 2Q. So these should kind of bend up and then all of a sudden come in. So that shows how much stronger that field is due to the 2Q than of the Q. So the Q can't push out much, but the 2Q can. We'll do the same thing on the other side, is we'll kind of get it bent. This one would bend and then come in. This one would bend a little bit up and then suddenly come in. This one would bend up and then suddenly come in a whole bunch there. And then we're going to do the same thing on the bottom. And we only come out a little bit before we come in. Just make sure your lines don't cross. And then also remember that these will loop out and come back around too. So we want to do a couple coming from the other side. Just to kind of show, they should also be symmetrical. So I've done 1, 2 here. I probably need to erase one of my lines that I have here since I only have 2 below. So let's just put 2 below over on this side. So we got this one still. And then I've got 1, 2, 3, 4 up top, and I've got 1, 2, 3 up top here. So let's add another one. Just want to make sure it's symmetrical in terms of the number of lines. So my drawing's not the best, but you kind of get the gist as to what's going on. For number 41, it says sketch field lines near 2 isolated and equal. Here we've got 2 positive point charges. So I'm going to put a positive charge and then another positive charge. And we know the field lines can't cross, but we know that these lines are going to have to repel because we have 2 like charges. So I always start with the ones that are going straight out, and then they bend very steeply at about a 90-degree angle. And so you should end up with some pictures that look like this. On this side, they will just go straight out because there's nothing interacting with them. Because they're the same, we do want to try to keep the number of lines the same on both sides. So I'm trying to make this as symmetrical as I can. And notice that you have an area in the middle where there's no electric field. That is letter A. For letter B, we have 2 negative point charges, and remember negative point charges, all the lines go towards those. So we're just going to do the opposite of what we did above. We're going to start away and go in. We're going to do the same thing here, And once again, we've got this dead space in the middle where there's no electric field. So we've got some that are curving in, and then we're going to have some that are pointing straight in from outside. So this one kind of curves in. We'll put that one straight. And then we just want to make sure we do the same thing on the other side so that it's pretty much symmetrical. And you get about the same number of field lines on both sides. And that is the end of section 16.4 problems.